Good evening, everyone. Welcome to a special evening session of ECE 2002. This is meant to be the lecture for Friday, the 15th of July, 2022. Just being recorded one night earlier, but for the rest of today, we'll just pretend like it is Friday instead. So one thing I want to do was finish out lecture set 5, but before we do we have any questions that we would like for me to answer? All right, didn't think there would be many questions. As a reminder, I have some lectures on YouTube for those who are interested. Quiz 4 will be conducted, Friday at noon until Saturday at 11:59 p.m. So please make sure you remember to take that. Homework 5 will be due on Monday. I'm trying to think what else is coming out. I think that does most of our announcements. Oh, I guess one thing will, and I should say this again at the end. We should be doing, if you have questions you want me to do as part of a review session, like I did last time, where I worked out certain extra problems, whether they were from the homework or were just sample problems. Say, for example, you want to see another example on how to do convolution, or you want to see another example of how to do a Laplace transform circuit with initial conditions, or something to that effect. Please send your suggestions through Piazza so that I can start working on them and have them ready to go at the latest by Thursday of next week. Someone asked, what are we doing tomorrow? We are not going to have lecture tomorrow. We'll just have office hours instead. So I will not be able to be around during the normal lecture time. So just remember to take your quiz if you normally take the quiz on Friday. All right, let's get started. So before we jump right into the fifth topic, bandpass response in second order systems, let's jump back to resonance in second order systems to review a little bit of ideas. Always good to do this little bit of review. So again, resonance is associated with an interaction between inductances and capacitances in the circuit. So where there's interchange of magnetic energy and electrical energy, you get resonance behavior. So specifically, the resonant frequency is the frequency at which the imaginary part of impedance or admittance goes to 0. So we looked at the series LC circuit, and the resonant frequency is just omega naught. So when we plug in Z of omega naught, we get that the impedance of the entire thing goes to 0 because there's no real part of impedance. When we looked at the series RLC circuit, we get that the imaginary part of impedance went away, so there's 0 reactance, but there's still a resistance RS in the series RLC circuit. So the resonant frequency was again omega R equal omega naught, where omega naught, remember, is the frequency of the sinusoid that you would get if you were to excite the circuit with a step function or an impulse or something like that. You would get, a continuous, oscillation at the natural frequency. And the resonant frequency happens to be the natural frequency because the resonant frequency is also the frequency at which, the imaginary part goes away of impedance or reactance. So in the parallel RLC circuit, very similar to the series RLC case, you'll get that the impedance is 1 over RP plus J0. This is, I mean to correct this error. This should be Y. Y is equal to 1 over RP plus J0. This should be a minus sign. Just issue that correction at the end of tonight. Or maybe I'll do it tomorrow. A parallel series CLR circuit. So this was a more complicated type of second order circuit. This was phrased more as a design problem where it's like choose the inductance that makes this circuit resonant at the applied frequency omega 1. So we found what the impedance was, or excuse me, the admittance was. So it's going to be j omega 1 c sub p plus 1 over j omega 1 ls plus rs using phasors. So we simplified the admittance using the complex conjugate. So, shucks, I really don't want to figure out what is real and what's imaginary by looking at a division. So I can get a fully real denominator by multiplying by the complex conjugate of the denominator. So we'll get rs squared plus omega 1 squared ls squared, which is purely real. And then we get a real part, rs over that, and an imaginary part minus j omega 1 ls over that denominator, which, can be grouped together to get this. So by solving when the imaginary part is equal to 0, that's the resonant frequency, which is different than the natural frequency, which the natural frequency would still be 1 over square root ls c sub p. And, I mentioned earlier that this, part under the radical acts like a correction factor to the natural frequency if you were to solve for ls using the natural frequency. But instead, L sub s is equal to this. Resonance frequency happens to be a frequency that maximizes power transfer. The natural frequency is the one that, the sinusoid oscillates at when excited with a step. Well, I should clarify that it would be what the undamped circuit would, oscillate at. There'd be a damped natural frequency instead. Damped, yeah. Damped radial frequency, I should say. And then we talked about the location of poles. So undamped circuit has poles on the imaginary axis separated by, 10 radians per second from the origin. And then along the 10 radian per second circle, we have an underdamped circuit being in the left half plane, with complex conjugate poles. The critically damped circuit has a pole of multiplicity 2 right on the real axis. And the overdamped circuit has a pole within the circle and outside of the circle on the negative real axis, such that the geometric mean of the poles lies on the circle. Remember, in this case, sigma p is going to be something less than negative 10 radians per second. For the critically damped case, sigma p is exactly negative 10 radians per second. And then, or I guess nepers per second, I should say. And then sigma p will be greater or less than negative 10 nepers per second in the overdamped case. So there's a whole lot of intuition to be built here. When you're studying for the exam to definitely spend your time to make sure you understand these concepts. Lecture set 5 in general is just a more concept heavy lecture set than the other ones, where there's a little bit more calculation aspect. Here it's more how do you apply various concepts. Before we go on, I wanted to explain where we got some of these Bode plot rules, but I'll first check if we have any questions. Seeing no questions about the review of resonance. Some people are asking, where do we get like these rules for poles where we get, an asymptotic change in slope to negative 20 decibels per decade, actual frequency being 3 decibels down from the intersection of the straight line segments, and then the phase plot behaving like this. 2 decades worth of negative 45 degrees per decade slope. So I'll go back to this slide and say we're working with a very simple circuit, a series RC circuit, which has, a pole at negative 1 over RC. Right? We've solved the series RC circuit so many times, you get lambda is equal to negative 1 over RC. So when you work out, in the S world, that's equivalent to a pole being at negative 1 over RC. So let's look at this a little bit closer. So let's say we're going to plot the magnitude response with decibels. So we take 20 times log 10 of this expression right here. So 20 log 10 of this is going to be, by logarithm rules, 20 log of 1 minus 20 log of the denominator, which is square root of 1 plus RC omega quantity squared. But 20 log of 1 is just 0, because log of 1 is always 0. And then when you take the natural log of a square root, the natural log of something to a power just brings the power out front. So overall, we have, 20 log 10 of the magnitude of h at j omega is right now equal to negative 10 times log 10 of 1 plus RC omega quantity squared in decibels. And so far, that's an exact approximation. However, we're going to make, that's an exact statement. Now we're going to make an approximation and say that RC omega 1 squared is much greater than 1. So we can further simplify this down to say negative 10 log 10 of RC omega squared in decibels. But again, the log of something to a power just brings that out front. So you're going to get that 20 log 10 of h of j omega equals negative 20 log base 10 of omega plus a k, where k is equal to a constant, in this case, negative 20 log 10 of r times c, because you can break a product into a logarithm, a sum of logarithms. But wait a minute, minus 20 log 10 of omega plus k, that's the same thing as saying y is equal to mx plus b, where the slope is negative 20 decibels, per decade. X is the log base 10 of omega, which, we're plotting with logarithmic axis, makes sense. And that k is just, how far up or down we have to shift, to make our circuit, to be in line with our circuit. So that is exactly why when we look at these rules for poles, we get this asymptotic slope of minus 20 dB per decade beginning at the critical frequency. So whenever we had like a pole, here we were here, going up, and then we shift down 20 dB per decade. So now it's a flat segment. But when we arrived at this pole, we noticed that the actual magnitude response was 3 decibels down from where it was. Where does that number 3 decibels come from? Well, if we go back here, what happens exactly when we plug in the pole? So omega is equal to negative 1 over RC. You're going to get 1 over square root of 1 plus 1, which is 1 over square root of 2. So if you take 20 log base 10 of 1 over square root of 2, plug that into your calculator, you will get negative 3.0103, so on and so forth decibels. So instead of saying negative 3.01, we just say negative 3 decibels. So that's what happens when you plug in at that point. You get, okay, instead of being, along the flat straight line segment, it's going to be, 3 decibels down from that. Now, why does the phase response, we say, okay, beginning 1 decade before and ending a decade afterwards, use a slope of negative 45 degrees per decade? Well, the negative slope should be pretty easy to tell, but why we can do that kind of depends on using the Taylor series expansion of arctangent, which is just a little bit of extra work. But as you can see, when we look at the actual graph, we could very well approximate it as that straight line ranging from negative, 10 to the negative 2 radians per second to 10 to the 0th radius per second. Does that make sense to more people? I sometimes forget that this is probably your first time dealing with decibels regularly. So hopefully that explains why we have numbers like negative 20 decibels per decade always showing up. It's not a choice. It is a result of the mathematics of the approximation. Same thing with 3 decibels. It's not a choice that, stems from, what we did before, but it's, the exactitude of the mathematics. The phase response is a graph of the offset of the wave. Precisely. So if I were to apply a reference cosine, by definition, phase offset is 0 degrees. What happens if we apply a cosine with 10 to the minus 2 radians per second? A very slow cosine wave. Well, it says we would basically get negative 6 or so degrees phase shift. What happens if we apply one at 1 radian per second? We would get one with a phase shift of negative 84 degrees. Any other questions? I just wanted to clear that up from the lecture on Thursday. So now what we're going to do is skip ahead to the bandpass response in parallel RLC circuits. So now we're going to talk more about RLC circuits. So for this parallel RLC circuit, we have the resonant frequency is equal to the natural frequency 1 over L sub, or 1 over square root L sub P C sub P. And the attenuation sigma P is equal to 1 over 2 R sub P C sub P. So we note that the admittance is going to reach a minimum value of at j omega naught at 1 over R sub P when we apply omega is equal to omega naught. The capacitor and inductor are going to appear as an open circuit due to resonance. Remember, when you're talking about inductors and capacitors in parallel, at the resonant frequency, they become an open circuit. If you have an inductor and capacitor in series, they behave like a short circuit at resonant frequency. So if you look at the input impedance, so you take, hopefully we are comfortable finding the admittance of an R, L, and C all in parallel. You'll get 1 over RP plus J quantity omega C sub P minus 1 over omega L sub P. Or if you think in S, you'll get 1 over R sub P and then plus SC plus 1 over SL. So the input impedance is just the reciprocal of the input admittance. You work it out mathematically and you get something that looks like this. So you get the S squared plus 1 over RP CP S, and then plus 1 over L sub P C sub P as the constant term. And then you get a 1 over C sub P S. So this bottom should, be very familiar looking. It leads to the characteristic equation we're all used to because it's the natural, it's the natural response of an RLC circuit. The fact that we have this numerator might be the only thing that's a little bit surprising, but if you work it out, the numerator should be this. And again, it's going to reach a maximum value of R sub P at omega is equal to omega R, the impedance this time. We call this specific type of transfer function, second order circuits are special. The only thing more special might be first order circuits because we deal with them so much, and I guess 0th order circuits because they're all we talk about in 20,001 basically with resistor dividers and such. But first order circuits, second order circuits are special enough that we should add some terminology. So we call this specific response a bandpass response because only a certain band of frequencies are going to be transmitted by the circuit without significant attenuation. So we note that S in the numerator means there's a 0 at the origin, and because there's a the order of the denominator is 2, the order of the numerator is 1. That means there's another 0 in square quotes at infinity, because this should go to 0 as we increase frequency towards infinity. In between, the effects of the two poles will be felt. So now we're going to have to deal with a bombardment of new terminology. This might be some of the hardest parts. So we're going to introduce 6 ideas, 4 of which have a very easy graphical interpretation, 2 of which are calculated from our graphical quantities. So we'll call h sub m the maximum of the transfer function. So our transfer function, I guess, is going to be Zn. So by our impedance response, magnitude and phase, the maximum of our transfer function is going to be r sub p. We'll call omega sub m. So right here where we have the thick vertical axis, that's going to be at omega sub m. That's the frequency such that, the magnitude response takes its maximum value. So here, omega m is equal to omega naught, which is equal to omega r, the resonant frequency. So we'll call omega L the half power frequency, especially it's called the lower one, and omega H the upper half power frequency. So they are where the graph takes on the value of hm over square root of 2, or where the phase response is equal to 45 degrees or negative 45 degrees. Either definition is okay. Most people prefer to think in terms of the magnitude response. And notice that at omega m, the phase is exactly equal to 0. The circuit behaves like a resistive circuit, adding neither phase lead nor phase lag to an output cosine. We're going to calculate 2 quantities. So B sub omega is the half power bandwidth, most of the time just called the bandwidth. So B sub omega is equal to omega H minus omega L. And we'll introduce a variable Q, which is the quality factor of the bandpass characteristic, where Q is defined to be omega m over B sub omega. So graphically, we have interpretations for a maximum, for the frequency that causes the maximum, and then for, omega L and for omega H. What's the interpretation of bandwidth and quality factor? So the bandwidth measures how wide the pass band of the response is. So, how wide this peak is, how broad it is. And then quality factor measures like how sharp it is, like on a graph, how sharp does it actually appear? Because since we plot on log scale, it may not always look very sharp. So as a rule of thumb, Q greater than 10 is considered a high Q system. It's going to have a very narrow peak because, this omega m is located a certain distance along the frequency axis, and B sub omega is basically, showing how wide the peak is. So it's going to look very narrow. And then the opposite, Q less than 10, is considered a low Q system, or at least maybe a moderate Q system with a broad peak. So it looks more like a more gentle bump and bell. What questions do we have? What happens at the cutoff frequency? So the name half power frequency is very telling. It is the frequency where compared to the maximum, you have half the power being transmitted. Because 1 over square root of 2, because you have to square it, it becomes 1/2 when you do a power calculation. You can also think of it as, where you get the steepest transition type behavior. It also defines what we call the pass band. So between omega L and omega H is considered the pass band of our response. It's where signals are passed with very little attenuation. Outside of this is the stop band, where signals will be attenuated severely if applied at those frequencies. Any other questions? You're welcome. So now we're going to endeavor to do a calculation of how to get the bandwidth, from our R's and L's and C's. So this is going to be a bit lengthy. We could figure out, we already have HM, which is just R sub P. We already have omega M, which is 1 over square root LP CP. We need to calculate omega L, omega H, and then the bandwidth from those things, and then the quality factor. So how do we get those things from R's and L's and C's? So let's just jump right in. So Zn in magnitude is going to be equal to H of M over square root of 2 when we apply omega H or omega L. Here I'm using omega H comma L in subscript to denote, it could be either one of those. Well, the impedance or the admittance magnitude is just the reciprocal of that, so square root of 2, and HM is equal to RP. All right, so what is it actually going to be equal to? So we know the admittance in magnitude is equal to square root of 1 over RP quantity squared plus in parentheses omega H comma L C sub P minus 1 over omega H comma L sub P all squared. This just comes from looking at our circuit and seeing what the admittance is. And then we're doing it at the cutoff frequencies. Well, now we have two equations for the impedance magnitude at that particular frequency. We can just relate them. So we'll go ahead and say, okay, we'll get, by squaring, we'll get 2 over RP quantity squared equals 1 over RP quantity squared plus something else. The only way you could get 2 of something equals 1 of something plus another thing is if the other thing is equal to 1 of something. So 1 of something being 1 over RP quantity squared equals this part right here. So we'll get quantity omega H sub L C sub P minus 1 over omega H comma L sub P quantity squared. Now you'll work this all out and you'll get a quadratic equation for omega H or omega L. Omega H1 has a minus sign right here. Omega L has a plus sign right here. And then furthermore, we know that the bandwidth is defined as omega H minus omega L. So right now, what we have to do is break out the quadratic equation to solve this. When you do, it's lengthy, and I really don't want to clutter the slides with too much of this, and it's something we only want to do once. You'll get omega H is equal to square root of 1 over 2 R sub P C sub P quantity squared plus 1 over L sub P C sub P, and then out of the square root plus 1 over 2 R sub P C sub P. And omega L is the exact same thing, just with a minus sign outside of the square root. Well, we know what these quantities are. We've already given them names before. 1 over 2 R sub P C sub P is the attenuation sigma sub P. And then 1 over L sub P C sub P is just omega naught squared. So we get omega H is equal to square root of sigma P squared plus omega naught squared, and then plus sigma P out of the square root. Omega L is equal to square root of sigma P squared plus omega naught squared, and then minus sigma sub P out of the square root. And then B sub omega is omega H minus omega L, but all the square rooty stuff cancels out, and we're just left with 2 sigma P, which is 1 over RP C sub P. So lo and behold, we have these nice exact values for omega H, omega L, and B omega, where B sub omega is really, really, compact when we write it all out. Is everyone with me? Will Q ever approach infinity when the magnitude response appears as a vertical line? Yeah. Yeah, I mean, Derek, you could say that like a delta function is basically uh, a Q equals infinity type of situation. I don't think most people would call it a true bandpass response, but like it is, something like that. Because you normally think about bandpass responses of having a maximum value, and you can't really do that with a delta function unless you're also changing the area under it, at which point it's no longer really a delta function. So if we work out the quality factor, so quality factor is just omega m divided by b sub omega, or yeah. So we'll take 1 over square root LC divided by 2 sigma p, and you'll get omega naught over 2 sigma p. Or if you work this out, you'll get R sub p divided by square root of L sub p over C sub p. And I specifically wrote it this way because I think it'll relate more to ideas we encounter later on if I write it as square root of L sub p over C sub p as one quantity rather than flipping it around and saying, R sub p times square root of C sub p over L sub p. This is definitely going to serve you well later on if you calculate these ideas separately. Now, there's, these equations for omega h and omega L are hardly used in practice. I mean, you can. I certainly use them when I'm being exact, which I try to be for lectures and stuff. But most of the time, people will say for a very high Q system, again, that's, rule of thumb, Q greater than 10 or so, Q being unitless, you will get omega h is approximately equal to omega m, the middle frequency, plus half the bandwidth. Omega L is approximately equal to omega m minus half the bandwidth. So this is a symmetric approximation. It basically says omega m should be the, arithmetic mean of omega h and omega L. So yeah, I guess this is the arithmetic. However, in reality, you go back to working this out, you'll get that omega m is really equal to the square root of omega h times omega L. It's a geometric mean of these two frequencies, these two cutoff frequencies. So the frequency at which the maximum appears, work this out. You multiply this by this, it's kind of like the difference of two squares types of thing. So you get sigma p squared plus omega naught squared minus sigma sub p squared, and you will get omega naught, which is equal to omega m. You do take the square root. Lastly, you don't even have to try that hard to get some of these things if you look at your transfer function very carefully. So if you look, the original transfer function was 1 over c sub p times s over s squared plus 1 over rp c sub p s plus 1 over lp c sub p. But this is already telling you a lot of your things. So like if I ask you for the bandwidth or for the natural frequency or undamped natural frequency, you should be able to get that immediately. Because this is just equal to, 1 over c sub p s over s squared plus the bandwidth times s plus omega m quantity squared. Or you can think of it as, 1 over c sub p s all over s squared plus 2 sigma p s plus omega naught squared. If you like thinking in terms of the original stuff we did when we were talking about second order circuits, where we defined sigma p and omega naught way back in lecture set 2. So this is thinking of it in terms of lecture set 2 material, undamped natural frequency and attenuation. This with capacitance involved. This is thinking of it in terms of the new concepts, which is the center frequency of our bandpass response, the bandwidth, and capacitance as well. Can't really get around that. What can I answer for you? How can I interpret some things? So AJ has a question. Is Zn supposed to be a transfer function or an equivalent impedance? Why not both? So, Zn is basically the ratio of, let me just think. Zn is equal to V sub C of S over I in of S. So it's a voltage to current ratio. So the output would be the voltage across any of these elements. I'll just say V sub C of S. And then the input would be a current source, I in of S. So input impedance is its own type of transfer function. Everything can be a transfer function if you define your output and input correctly. Does that help, AJ? You're welcome. Now, anyone need help interpreting, the cutoff frequencies, the bandwidth, or the quality factor? So like I said, we went through the effort to explain what they were graphically and how to calculate them. We talked about the interpretation, a little bit of them, and then we went through the effort of finding omega L, omega H, B sub omega, and Q in terms of R's and L's and C's. And then the result of it was we found out that our transfer function basically gives away, two of the hard things to find. And then, well, you can easily find Q from this if you need to. Finding omega L and omega H requires a little bit more effort, but if you do the symmetric approximation, if Q is big enough, you basically get everything from the transfer function. You don't need to go through the calculations. So on the homework, unless it specifically tells you to do so, please don't go through the trouble of recalculating all this stuff. If it's a strictly parallel circuit, just interpret the transfer function accordingly. It's worth the time to memorize, these two interpretations of the transfer function. These are things you should, try to commit to memory. More so the denominator than the 1 over CPS in the numerator. But you need to know that there's an S in the numerator in order to be what we call this bandpass response, corresponding to the underdamped circuit. Did I write that down anywhere? Oh, that's coming up soon. Oh. I gave away something. Whoops. Spoiled the surprise. When is omega m not equal to omega 0? If you have a circuit that's not purely in series or in parallel, omega m is not equal to omega naught. It's not equal to omega r. All three frequencies are different. I'm pretty sure. Or at the very least, two of them are different. Because we already showed that, omega r is not equal to omega naught in the parallel series CLR circuit. So I think omega m is also different in that case as well. Or it might just be omega r. Yeah, it's omega r is equal to omega m. So final answer, in a circuit that is not purely in series or in parallel, you will get like parallel series combinations of the resistor, inductor, and capacitor. You will find that omega r equals omega m. However, that does not equal omega naught, which is always going to be 1 over square root LC. You have to figure out where the circuit resonates in order to find, where the imaginary part of impedance or admittance goes away. And that will be the place where you have your maximum of your transfer function, because the maximum of the transfer function is where maximum power transfer occurs, which happens at the resonant frequency. But very good question. I had to think about that one. So let's talk about the bandpass characteristic of RLC circuits. So we'll look just at the magnitude response. The phase response, I'm going to leave out. I mean, if you're so interested, plot phase response on your own. I think that's going to be my instruction. But speaking of plotting on your own, for this first graph, my plotting utility I used to make these slides completely objected. It does not like it when things blow up to infinity. And that's exactly what's happening. You'll notice the scale is very different here. And it just stops when we get too close to 10 to the first. That's because it just cannot plot it. It's discontinuous. There's a vertical asymptote, and it just doesn't like it. So at the underdamped circuit, so I specifically chose, with omega not equal to 10 radians per second. Let's just say we have, something that looks, fairly narrow, but it's still considered a quality factor of 2.5. It's still considered a low Q circuit. So this one is going to have, sigma p is equal to 2 nepers per second. Omega d, the damped radial frequency, I should say, is 9.798 radians per second. And then the bandwidth is 4 radians per second. So, it definitely fits here. So, when we talk about, what happens if we, let the circuit, relax a little bit further. So we increase the R a bit more. We'll get, for the same omega naught equals 10 radians per second, maybe negative 6 nepers per second plus J8 radians per second. Well, the bandwidth is now 12 radians per second. And already that's kind of suspicious because we're saying the bandwidth is greater than our center frequency. So this is a Q less than 1 type of scenario. Some people don't like talking about bandwidths that are bigger than their resonant than the center frequency. You might argue that there isn't a nicely defined bandwidth for this circuit. It's too broad, but you could still say that's quality factor is 0.833. That's engineers disagree about how to phrase these sorts of things with second order circuits. And then as we go farther, we have the critically damped circuit. Its magnitude response looks like this. Still a little bit of a bandpass response. We'll say the bandwidth is now 20 radians per second, which is twice omega naught equals 10 radians per second. And the quality factor is 1/2. So this is a very, very low Q system. It doesn't even make sense to talk about bandwidth past this point if you lower the quality factor anymore. So the one thing you should remember is that, and I don't stress this enough, you always have this relationship where quality factor equals 1/2 is always the case for a critically damped circuit. So when we talk about, high Q systems, we're really talking about a subset of underdamped circuits that are very, very resonant. So from now on, we're going to focus mostly on the underdamped case, with imaginary roots, and neglect the part where we have real roots because they don't behave nearly as interestingly for the purposes of, bandpass filters, or what we're going to talk about coming up, which are, low pass and high pass filters. So unfortunately, the curriculum just does not leave time to talk about how to design a good Butterworth or a good bandpass or band reject circuit. We will mostly focus on the analysis side of things. And that's kind of, we just don't have, enough weeks to talk about it. Yep, they're both underdamped circuits. The second one on the right of slide 44 and the first one on the left of slide 45. They're both underdamped circuits. They just have different quality factors. One is the, bigger Q circuit. One is the lower Q circuit. And you can see how the peak gets less and less broad. Or gets broader and broader, I should say. Does that answer your question, David? Yep. Okay, good. So as we have done in this course, whenever we talk about the parallel RLC circuit, we want to jump into the series RLC circuit and talk about similar things with duality. So again, omega naught is 1 over square root. This should be L sub S, C sub S, with sigma P is equal to R sub S over sigma or L sub S, 2 L sub S. Wow. Sigma P is equal to R sub S over 2 L sub S. So the impedance reaches a minimum value at R sub S. Capacitor and inductor pairs a short circuit due to resonance. The inverse of impedance is admittance. So the input admittance is 1 over L sub S over S squared plus R sub S over L sub S times S plus 1 over LS C sub S. So its maximum value is 1 over RS at omega is equal to omega R. Bandpass characteristic. Only a certain band of frequencies are transmitted. The ones in this pass band between omega L and omega H. Whereas anything outside of the pass band gets attenuated severely. There's a 0 at the origin. So at frequencies close to 0. And as omega goes to infinity, you also get 0 transmission. In between the two poles cause this bump to be felt. So from the graph, H sub M is 1 over RS. Omega M is equal to omega naught for this purely series circuit. Omega L is equal to this exact thing. Omega H is this exact thing as we calculated before. And B sub omega is R sub S over L sub S, which is equal to 2 sigma P. And Q is equal to 1 over RS square root of LS over CS omega naught over 2 sigma P. And we'll get omega H approximately equals omega M plus half the bandwidth. Omega L is approximately equal to omega M minus B sub omega over 2 as our symmetric approximation. And the exact geometric mean interpretation, omega M is equal to square root of omega H times omega L. And our input admittance transfer function behaves very similarly, where you can think of as 1 over L sub S times S. Again, that just kind of hangs around in the numerator. No real interpretation to it. A denominator of S squared plus B sub omega S plus omega M squared. Or using the old ideas, S squared plus 2 sigma PS plus omega naught squared. There's no reason why. It just happens that if you look at these two numbers, because of the nature of the quadratic equation they satisfy, if you square them, or excuse me, if you multiply them together and take the square root, you just get omega naught. So there's no reason why you use it. It just happens to obey that relationship, Aubrey. Would be expected to do this with a different type of circuit, like not completely series and parallel. How exactly will we do that then? That's a good question for homework. you would go through and find, okay, how would you find, these types of equations? So I gave you the bandwidth calculation to find omega h and omega L. You would actually have to go through the math, figure out what omega h and omega L satisfy, and you would get very similar relationships to what you see here. In fact, since this is in the denominator, you expect this to behave basically the same way as it would for a purely parallel or purely series case. I will say, AJ, like, that's a good question. Something you'll probably explore on homework, though. All right. Last slide of the lecture set. Oh, one more thing. It says impedance response should be admittance response. That'll get corrected in an updated version of these slides. And again, never replace the slides you take your notes on. Just, I give you slides for posterity's sake. What happens if we do frequency scaling? So we introduced all these new concepts. How do they change when we do frequency scaling? Remember, impedance scaling doesn't change the transfer function. So all these transfer functions, I should say magnitude scaling, will change the units. So, it'll get a 1 over km for, the admittance and a km times it for the impedance transfer functions. So we know how those behave. But how does a frequency scaling affect everything? So if we want a new frequency, omega prime equals kf times omega. So the undamped natural frequency is scaled up, as you would expect, because you want to scale up all your frequencies. The two cutoff frequencies and the bandwidth are scaled up. So omega h is equal to kf omega h, omega L prime is equal to kf omega L. Then your new bandwidth is going to be the difference of your new cutoff frequencies, which is kf times the difference of your old half power frequencies, just factoring the kf out of both of them. So you get your bandwidth goes up by a factor of kf. Your quality factor will stay the same. So q prime is going to be new mid center frequency over new bandwidth. So you'll get kf omega L over kf b sub omega, which is just q. So the graphical interpretation of this is that the entire transfer function gets stretched horizontally. So it's going to move, everything and stretch things out horizontally so that, your center frequency moves, your omega L moves, your omega H moves. But it's otherwise the same looking. So on a logarithmic frequency axis, stretching out is just the same thing as translating the whole thing right. And the shape will be completely unaltered on a, log-log type plot. So this is, a huge deal. So if we ask you, okay, here, plot the transfer function magnitude response and phase response, and then we say, okay, now plot the magnitude response after you apply a frequency scaling of kf equals, I don't know, 9 times the square root of 51. You know that, okay, you just add whatever 20 log 10 or whatever log 10 of, 9 square root of 51 is to everything, but all the shapes will stay the same. And with that, we are done with frequency response until we talk about it again in the next lecture set, and then we talk about it again in lecture set 7. So this isn't going away anytime soon. Do we have any final questions? If not, I officially announce that this is the end of the material that will appear on exam 2. Study well, ask questions, let me know what types of problems you want me to see me work out. I know one of the complaints about this course is there's a shortage of worked out examples. So please let me know what examples you would like me to work out. With that being said, class dismissed. Goodbye, everyone.